Okay, good morning. So, as Michael shared, he just made a discussion post in the Choose Your Organic Molecule.
It's just its own separate discussion post.
Oh, I didn't even think I had discussion boards open. Are you able to just make a discussion board? Oh, there, yeah.
Yep, there it is.
Learn something new every day. Michael just made a discussion post with a link to a resource that comes highly recommended. So take a look at the discussion boards to find that resource. I also wanted to talk to you about your analysis assignments. 4 have already been submitted. 2 of you guys in the room. Can I ask you, well, I guess I wanted to frame it like this first. I want you guys to pick something that is relevant to your career path or your work, your field. Like if you work in a pharmacy, think about prescription drugs that you deal with a lot and submit 1 to 3 of the compounds to be analyzed. We're going to apply course concepts throughout the semester to this. I have actually, I started this series, like this type of assignment as a makeup activity, a bonus point activity. And then the reflections I got from students was that the assignment was so effective at helping them understand course concepts by applying it that I decided to make it a course-long project. So now students pick a compound of interest to you and apply the class concepts to it. I can give you molecules all day, and I will. But it's different when you choose the molecule and start applying things to it. So please submit that. I think it's due tomorrow. See if you can find some time today to look through compounds. Now, how did you guys narrow in on compounds to submit for? Did you submit 1 or 3?
3.
Great. I love that because especially in OChem 1, there's a lot of molecules we can't actually apply our reactions to. And the more options I have, the more likely it is that I can find a molecule that we can do a reaction with. How did you find your molecules?
They're used at work all the time.
You use them in work in the hospital. Same with you?
Yeah.
They're just things that you cross by all the time. You've never really analyzed them, but you're interested in doing it for this? Great. I also recommend, if you're not sure even where to start, ask an AI bot. I'm in this field. My professor wants me to analyze an organic molecule relevant to my field. I'm not sure where to start. Could you give me 5 compounds that are related to this field, would work good for this project, and then give me a link, either a link to the PubChem information about this molecule, or a link to an image about this molecule, or a link to an article that talks about how this molecule is used in research. If you're not sure where to start, AI is a good tool to help you figure it out. But I love this assignment because I get to hear your thoughts and see what you're learning. So I don't really encourage you to just plug this into I'm not interested in seeing AI's take on this assignment. I'm interested in your take on this assignment, but leverage AI if you need help with a launch point, yeah? Something I forgot to mention to you guys yesterday, and this really impacts, I shared this with my other section, but it really impacts you. In the last 2 weeks of the semester, or really the week before finals, where we'll just be doing a review. In the last 2 weeks of new content, our last unit, I will be on my honeymoon. I'm getting married mid-June while you guys are taking a unit test. And then we're going on our honeymoon in late July. So I will be gone. I'm currently subbing for another professor for these first 2 weeks of the semester. And she will be subbing for me in the last 2 weeks of the semester. Now, this part of the semester is all reactions and synthesis, which means take one thing, turn it into another, turn that into another, turn that into another. And in that area, you're going to have your last analysis of an organic compound assignment, where you apply reactions that we're learning to your compound. Because again, I can give you compounds to show how they react, but I want to see how you can apply it to something that you're interested in. So I wish I were here because it's the best part. I'll be back to do our review days together. And I'm going to have materials prepared because, to be honest, at this point in the semester, a lot of what you need is the information in one place that you can reference as you apply it in practice problems. There's not a lot of explanation I need to do. I've done a lot of explanation in the past, and students have told me, you could have talked a little less and given us more time with just the resources to solve things. So you'll have a great professor subbing, but I will be gone those 2 weeks. What else? How many of you have had a chance to explore Canvas, explore Active, explore other stuff? Anything you're curious about? Anything you've got questions on as we are diving into the class? One thing that I'm doing, I'm doing this right in front of you so you all see it. I'm actually bringing my old 2310 materials right up to the front. This has my old supplemental work problems, my old homework problems, and my old detailed PowerPoints. If you're one of those students that actually likes having detailed PowerPoint slides, that's how I taught my very first semester. I just got sick of it eventually, and I don't use them anymore, but they're there. So if you want to use them, feel free. And now I'm bringing it to the top because I want them to be one of the first things that you see when you're scrolling through Canvas. Okay. We kind of touched on this last class, but I'd like to hear from you guys about what you think organic chemistry is. Sorry, I know I'm handing them out a little bit weird. If you could just pass those down, please. The front page should be atoms, ions, and molecules. I need to put page numbers on these things. What is organic chemistry? What is chemistry? Okay, what is biology? Wow, okay. So you know what biology is, but you don't know what chemistry is. Okay, I heard there were some good ideas in there. Study of chemicals, the study of chemical interactions. Maybe a little bit too specific, I think, actually, to say the study of chemicals, because what is a chemical? Study of molecules might even be equally as specific. Chemicals are molecules, sometimes, maybe sometimes not. But all of those have something in matter, something in common, something more broad. It's matter. Chemistry is the study of matter. And its interactions and the changes that matter undergoes. Chemistry is evaporation. Chemistry is condensation. Chemistry is hydrogen bonding. Chemistry is redox reactions. Chemistry is a nuclear fission, nuclear fusion. That's chemistry. If it's matter and it undergoes a change, it's chemistry. When electrons get excited by light, it's chemistry. Organic chemistry was defined once as the study of hydrocarbons and their derivatives. Actually, organic chemistry originally was recognized as those compounds which derive from life. There's a lot of compounds in the world that old chemists used to think, old chemists is maybe the bad way to say that, leading chemists, pioneering chemists, used to think were only created by life. Like urea was only created by living compounds, biological compounds. Proteins, cells, things that make up the body, these things were only made by living things. So they called all of these carbon-containing compounds made by life organic. And then it wasn't until the mid to late 1800s that chemists actually took inorganic starting materials like nitrogen, N2, and carbon dioxide, and potassium hydroxide. And they took all these inorganic reagents and they made organic compounds. The synthesis of urea, which is a relatively small compound. And I know that this structure has a lot of assumptions going on. We'll talk about bond line structure soon. The synthesis of urea from strictly inorganic reagents was the proof that organic chemistry doesn't need life to exist. Organic chemistry is just hydrocarbons and their derivatives. You'll notice that this compound, well, you won't notice it because I made this one silly assumption. This compound actually isn't a hydrocarbon. It has no carbon-hydrogen bond anywhere in the molecule, but it's a derivative of a hydrocarbon. It has these heteroatoms, things that aren't just hydrogen and carbon. And this is actually an example of us as chemists drawing lines in the sand and saying, on this side it's organic chemistry and on that side it's not. And there are these really confusing molecules that blur the line. Something like carbon dioxide, no hydrogen. So is it a hydrocarbon derivative or is it inorganic? Things like carbonic acid or urea have no bonds between carbon and hydrogen, but they have both carbon and hydrogen. So is that a hydrocarbon and a derivative, or is it inorganic? Not clear. So if you're ever confused about whether something's an organic molecule or not, you might not be alone. It might fall into that blurred area. So let's take a look at all of the different types of chemicals that we make. I want to start with just an overview of the atoms. Where do we find our atoms? Or a reference about our atoms, I should say? Periodic table is a great place to look. Periodic table is organized by what characteristic of atoms? Kind of. Electronegativity, I think, is coincidental. I don't think the periodic table is arranged by electronegativity, but electronegativity coincides with the periodic table. I don't know that I would say that the periodic table is organized by valency or electrons, but not a bad idea. Not quite by mass either, Saray. Protons. We organize it by the number of protons in the nucleus. So atoms are composed of two parts. The first is the nucleus. With protons and neutrons in it. So the nucleus is a net positive particle because it's all just one discrete unit. The nucleus has all of the mass. That's a lie, but it's an okay lie. You know, it's like saying that the egglet on my shoestrings. You guys know what the egglet is. You all watched Phineas and Ferb. It's like saying the egglet doesn't really make any of the mass of me today, because my body mass compared to the mass of my egglets is just so much greater. My egglets are insignificant. There are electrons do add mass, but it's like 1,000 electrons to 1 proton. So essentially all of the mass is in the nucleus. What is the other part of the atom? The electron cloud, where we find the electrons. With, of course, the electrons. This electron cloud is organized. I want to talk about that just underneath here. Organized into different ways that the electrons appear. So this, of course, the electron cloud is a net negative region, and it composes all of the size of the atom. I want you to think about that for a second. The atom is made up of 2 regions, the nucleus and the electron cloud. The nucleus is where all the mass is, and the electron cloud is the entire size of the atom. You guys know how big the solar system is? Space is sometimes a good analogy for us. Anybody know how far Pluto is away from the sun? Far. I think Pluto is like 1 billion miles from Jupiter, and Jupiter is like 1 billion miles from the sun. I don't have those numbers. Hey Siri. So, solar system is huge. We could say that the orbits of the planets make up most of the size of the solar system. But where is all of the mass in the solar system? Relative to the sun, the sum of all of the planets is just insignificant. So the sun is all of the mass of the solar system, but the planets make up all of the size of the solar system. The size of an atom is more astronomical than this literal astronomical example. If the atom were the size of the state of Colorado, which I think arguably would be about the size of the state of Utah, the nucleus would be the size of a basketball. So you've got a basketball in Fillmore, Utah, and you've got electrons that are riding the Idaho border, the Nevada border, the Arizona border, the Colorado border. And they're being pulled in by the positive charge in Fillmore. If that's not crazy to you, think again. That's crazy. That is a huge thing. So when we talk about atoms, and we're talking about the size of an atom, we're talking about its electron cloud. When we're talking about atoms butting up against each other, we're talking about electron clouds butting up against each other. We're not talking about nuclei interacting. In fact, if you wanted to argue why electrons and protons, which are attracted to each other, never actually hit, it's because you've got the pinhead of a needle flying around the borders of Utah trying to hit a basketball in the middle of the state. You could shoot that pinhead from the borders and try and hit the basketball, but good luck. Like, that size is huge. Just because it's got that electromagnetic attraction doesn't mean they have the probability of running into each other, right? Okay, enormous difference. Now, the electron cloud is broken up into orbitals. Orbitals, I want you to define it, please. You've all taken chemistry. You know what chemistry is now. What's an orbital?
Like a layer that contains a certain amount of electrons.
A layer that contains a certain amount of electrons. Maybe. Layer makes me think of the energy shells. Layer is a bit of an ambiguous term, I feel like, here, but I like the idea. Can we add to it? The idea of where the electrons are is good.
Specific shape.
Shape.
The electron cloud has depends
The shape differs in different types of orbitals. The orbital is actually a mathematical equation. Did you know that you could make a mathematical equation for a wave in the ocean? I mean, you can use like sine, cosine, or whatever, but you could have an equation that describes how a wave propagates. And electrons aren't particles any more than anything else is, but they're as much waves as they are particles. And we want to describe the nature of the wave, how the electron behaves. So orbitals are mathematical equations that define 95% of the probability region where an electron is. Orbitals, so math equations with size, shape, and orientation. If we create an x, y, z coordinate axis, we could actually have orbitals of the same size and the same shape, but oriented differently. When we look at orbitals between energy shells, we see orbitals of the same shape and orientation, but of different sizes. So the math just changes. That's all it is. And because we're looking at the math that describes an electron, some orbitals need to have different explanations for when the wave is going up versus when the wave is going down. So we represent that with shading. A shading says the mathematical equation starts with plus. And here, the mathematical equation starts with minus. If I'm monitoring a wave in the ocean, I want to be able to describe the difference of the wave cresting versus the wave troughing, right? I want to know when the wave is pushing up versus when the wave is pushing down. And shading is what allows us to do that. And we say it's 95% the probability region because the rest of the 5% of that mathematical equation extends to infinity. There is a non-zero chance that one electron on your body right now could instantaneously be on the moon. And the moon is, we just saw the Artemis mission, the moon is not close. But instantaneously, you have an electron that could be on the moon. There's a non-zero chance, it's a much smaller chance, but there's a non-zero chance that every electron in your body is instantaneously at the moon. That's weird. And it gets really hard to represent. To draw this but show that it extends to infinity is impossible. So we lob off that last 5%, and we just say, this is 95% of where it's most likely to be. This size, this shape, this orientation. There's other information here about nodes in these orbitals. This is a node. So if you're looking at a wave in the ocean, you would say the node is where the wave doesn't exist. That part of the wave is level with baseline ocean height, right? Like, is there really a wave right there? If all you could see is zoomed in right on that part of the wave, you wouldn't know that there is a region higher and lower than that. You're just looking at the baseline. So we say that the node is where the wave doesn't exist. We say the node is where the wave changes sign, where it changes phase. So these are different phases or signs, plus minus, going up, going down. And the node is where the wave doesn't exist because it's changing phases. So we're looking at the same thing here. These are our phases, and this is a node right in the middle. Now, just like waves in the ocean, even with sound waves, waves of light, waves can constructively interfere and they can destructively interfere. if waves come together in phase, then they appear as the sum of the two mathematical equations. If waves come together out of phase, then they come together as the difference of the two mathematical equations. Orbitals are just mathematical equations that describe the nature of the electrons in them. Okay? In an atom, and what we're referring to here is like a free atom. We learn that the orbitals are 1s, 2s, and 2p. You recall this? The s orbital has what shape? Spherical. Spherical is a great way to remember it. We say that the 1s orbital has 0 nodes. As I move up into higher energy shells, each s orbital gains a new node. It's in the second shell that the s orbital gains a spherical node. That means there is a sphere inside of a sphere. And notice that the phasing changes, because at a node, the phase changes. So the inner sphere is going up or going down, and the outer sphere is the opposite. That's called an angular node. I'm sorry, a spherical node. All orbitals in the same energy shell have the same number of nodes. If you look at the second energy shell, there's always one node. Third energy shell, always 2 nodes. Fifth energy shell, 4 nodes, so on forever. It's because it's all math. It doesn't end at the periodic table. It goes on forever. So the 2p orbitals also have a node, but their node appears as an angular node. And the orientation of the 3 distinct orbitals in this subshell are distinct. Three different nodes. Oh, sorry, I meant to say these are angular nodes. As I move up to 3p, I still have one angular node. The p orbital is defined as having an angular momentum or an angular node of 1. So every p orbital has one angular node, this cut through it. But as I move up to a higher energy shell, the p orbital gets a spherical node as well. You don't have to draw this one if you don't want to, because it gets a little challenging to draw. But if I could cut into it the same way that I cut into, whoops, I shouldn't have done that color. Same way I cut into 2s. We would find that there's a spherical node sitting on the inside. It's another p orbital on the inside of a p orbital, separated by this spherical node. P orbitals have one angular node. Each increasing energy shell adds an angular node. Man, I say it wrong every time, huh? P orbitals always have one angular node. Each increasing shell gets a new spherical node. Said it right that time. It's beautiful stuff. Waves are beautiful. There's a reason that people like long walks on the beach, and it's not because the ocean is quiet and still. People like long walks on the beach because of the waves. So, electrons are always defined by these waves. When we look at a free atom, these are the orbitals that we think of. But these atoms will often hybridize once they get into bonding. So we're going to take these orbitals, these mathematical equations, and we're going to mix them together and get new mathematical equations, new shapes, new sizes, new orientations, the sum of different mathematical equations coming together. All right. I think before we move on from here, we can talk about the valence electrons, because this will be an important thing about our atoms. Did you guys know valence is Greek for strong or mighty? Why do you think we would refer to certain electrons as the strong electrons? What are valence electrons known for?
Like being on the most outermost shell.
These are our outermost electrons, the highest energy electrons. The electrons that are given or taken during redox reactions, the electrons that are shared in chemical bonding. These are the strong electrons because they are the ones that do everything. These electrons are responsible for all of our chemistry. And they're only found in the outer shell. So let's go through some of our most common elements. And let's talk about their valence electrons. If you need a periodic table, I'll just project one up onto the screen. Eventually, this is going to become something you need to memorize. Well, do you know the difference between memorization and familiarization? Like, do you think I've memorized my route home from school? I had to sit down and memorize the roads and memorize the turns.
It's like memorization is a sheer learning of that same thing, whereas familiarization is an association with the things around it.
Perfect. Memorization is recall. Familiarization is recognition. There is a distinction between the two. Recall is, I've seen that, and this is what I associate it with. Recognition is, I've seen that because I've used it in these situations. Okay, I've got 3, 6, 9, 10. Can I get 10 people to give me valence electrons? Who wants to start with H? How many valence electrons? Saray? 1. Who wants to start with, or who wants to give me boron? 3. Carbon? 4. Nitrogen?
5.
Oxygen?
6.
Fluorine?
7.
Phosphorus?
5.
Sulfur?
6.
Chlorine?
7.
Bromine?
7.
Iodine?
7.
That was really fun. That was not 10 of you, though, by the way. That was all of you. So, okay. One of the most common mistakes is flipping the way that we think about how many extra electrons it needs. For instance, nitrogen wants to gain an octet by gaining 3 extra electrons. We call it a trivalent atom because it makes 3 bonds and because it wants to gain 3 electrons. But that doesn't mean it has 3 valence electrons. It's trivalent because it wants 3 extra valence electrons. Oxygen and sulfur are divalent. The halogens are monovalent. Hydrogen is monovalent. Boron is surprisingly trivalent as well, despite the fact that you'd think it wants 5 extra electrons. We'll get into that when we do formal charges in a minute. Okay, moving on from atoms. That's pretty foundational. Pretty basic stuff, yeah? I want us to compare molecule versus compound. Are they the same word or term, different words for the same idea? Or are they distinct? What's the difference, if so? Mackenzie, you were shaking your head.
Like a compound is when there's like bonds between like the same type of atoms, like oxygen to oxygen, while like a molecule is bonds between different atoms, like an oxygen to a hydrogen. What did I get? Like,
What do you think?
I have it right.
Compound, meaning bringing two things together, like a compound word brings two different things together. So compound, think different. If it's not different, it's not a compound. So oxygen bonded to oxygen, not a compound, because it's the same element bonded to itself. In fact, oxygen bonded to oxygen is an element, despite not just being a single atom, it's just the element in its most stable form amongst itself.
Is that diatomic?
A diatomic element. Sulfur also forms an element, but it's like octatomic. S8, it forms this like weird 8-membered ring of sulfur. That's sulfur in its most stable form. Oxygen, hydrogen, nitrogen, the halogens, all diatomic in their most stable form. Molecule describes multiple atoms being bonded together. Compound describes different atoms bonded together.
So all compounds are molecules, but not all molecules are compounds.
Maybe, because then we can also refer to ionic compounds. Like sodium chloride is an ionic compound, but it's not a molecule. So there is some overlap. There's, I guess, a Venn diagram of them. Some compounds are molecules, but not all compounds are molecules. So molecule has covalent bonding. Compound has multiple atoms or multiple elements. Notice how molecule doesn't need to have multiple elements, and compound doesn't need to have covalent bonding. But there can be an overlap. So we already named a few, like H2, N2, O2. And if I write X2, what do I mean? Not xenon. No, xenon is Ze. X2, no, not any element, but I'm glad you said that. We are referring to a class of elements, a family of elements. It's not a bad idea to think that X would just mean something, but we almost always reserve X for a family. What other family is largely diatomic? They're on the board. The halogens are largely diatomic. Fluorine is F2, chlorine is Cl2, bromine is Br2, iodine is I2. I don't know that people really consider At and Ts to be halogens despite being in the same family. Their metallic character has really increased at that point. So X2, take that note. X2 is halogens. If I wanted to say something like sodium chloride, potassium hydroxide. Trying to think of other ionic compounds, especially ones that will be relevant to us this semester, but things you've probably seen. No, I don't know. I really can't think of anything else off the top of my head. Sodium, oh yeah. Well, any other of the halogens, sodium iodide.